Hello, we are Group 17, and our project is Rocket Nozzle. And my name is Xie Changlin. So, what is a nozzle? Nozzle is a device designed to control the direction or characteristic of a fluid flow, as it exits or enters an enclosed chamber or pipe. A nozzle is often a pipe or tube of varying cross-sectional area, and it can be used to direct or modify the flow of a fluid like a liquid or gas. It can expand and accelerate the combustion gas produced by burning propellants so that the exhaust gas exceeds the nozzle at hypersonic velocity to high supersonic velocity. How does the nozzle work? During the combustion of fuel, chemical energy is converted into thermal energy and pressure energy. The combustion gas at this stage are at a high pressure and temperature, and this gas under such high pressure expands through the nozzle, during which the pressure energy is converted into kinetic energy, which in turn moves the vessel in the direction opposite to that of the exhaust gas, according to the Newton's third law. And what is the function of the nozzle? First is to remove combustion gas and heat produced by engine when burning fuel. Second is to provide sufficient thrust energy for the rocket to reach outer space.
My name is Guo Pei Liang. The constraint in our nozzle is mainly the cost and thermal conductivity. Our objective is to use reusable materials which are eco-friendly and has long durability. Our nozzle should be rust resistant and also thick. After launching to space, the outer parts of the nozzle will be removed from the rocket and will be dropped into the ocean, which will float and let ships search for them. That is why our materials should be rust resistant, as they will have to stay in the ocean for a while. Why thick? Rocket's gaseous product's temperature is a lot higher than the nozzle's temperature itself. There will be some parts of the nozzle wall that is melted and burned away. The current standard rocket nozzle can be reused up to 8 times. That is why our nozzle should be thick for later use. These are our formulas and design of nozzle. Thrust is produced according to Newton's third law of motion, and it depends on the mass flow rate of the engine, the exit velocity of the exhaust, and the pressure at the nozzle exit. The smallest part with the letter A on the nozzle is called the throat, which chokes hot exhaust flow, making the gamma or specific heat ratio equals to 1. Our next speaker is Dang Han Bin.
In this section, I will try to calculate the rocket thrust. And then, as you can see, I write there the rocket thrust equation. F equals to mass flow rate times exit velocity plus exit pressure minus atmospheric pressure times exit area. So, the bigger F is the stronger force coming out from rocket nozzle, resulting rocket accelerate faster. And to maximize F, the thrust energy, we can maximize the exit pressure and the exit area. Why I don't consider to maximize the mass flow rate and exit velocity? Because mass flow rate and exit velocities depends on what fuel the rocket use. And then we want to design the nozzle, so I don't consider it. And for atmospheric pressure, it is constant, so we cannot change it. So as we know, the function will reach its maximum value at slope equals to 0. And I plot it there. So we know that differential of F divided by differential of exit area equals to 0. And then I write the differential equation for the thrust force equation. And then as we can see, there are so many constants there, like V0 is constant, mass flow rate is constant, atmospheric pressure is also constant. But so after we know what constant is there, we will try to eliminate the element that including the constant there. So we will achieve a more simple version of the equation. And then I try to put mass flow rate equation into the simplified equation, and we got a new form there. After realizing that we can separate AE on the new form, we found that there are mass conservation plus momentum at exit equation. Derivative of exit pressure plus exit rho plus exit velocity times derivative of exit velocity equals to 0. So we can remove it because it equals to 0, and then we achieve a really simple version that derivative of transverse equation divided by derivative of exit area equals to exit pressure minus atmospheric pressure. And then we know in the beginning that derivative of transverse equation divided by derivative of exit area equals to 0. So at maximum thrust, pressure at the nozzle exit must be equal to atmospheric pressure at sea level because rocket launches at sea level. And then we know that atmospheric pressure at sea level is 101.325 pa, which is it's really high, and I think it's almost impossible to achieve exit pressure that equal to atmospheric pressure. So I think the conclusion of this calculation is we must to design the exit area as efficient as possible so it will generate the maximum exit pressure. And here I use SpaceX Falcon 9 for the example of rocket thrust nowadays. So I write the equation and get some data that nowadays rocket for Falcon 9 the exit thrust at initial launching is 6,419.8372 Newton, which can make the rocket get acceleration for about 2 meters per second. So here are some criteria for suitable material for rocket nozzle. And I also found out that why we cannot use aluminum on rocket nozzle, because aluminum is commonly used in car or motorcycle exhaust. I think it's because aluminum cannot withstand the really extreme heat and pressure on the rocket nozzle. And what common material used now is mix of titanium carbide, tungsten, and graphite. And heat at rocket nozzle is around 3500 Kelvin, which is very high, and I don't think that titanium can withstand it, but I think it's not a big matter because there is cooling system on the rocket. So if material is not good enough, we can improve the cooling system. For the material selection, as we can see, we need a strong material. So on this bubble chart, we look for material with modulus higher than 100, and then we found some metals there. And then we also need a material with high melting point. So based on this chart, I will consider silica, ceramic, carbon, and tungsten as the material that is suitable also. This chart of Young modulus and cost. So as we can see, we need a cheap cost material with high Young modulus. So and then the material is also the same, it's metals. And then I found out there are some suitable material. The material are titanium, tungsten, silicon carbide, and graphite. So the rocket body will mainly use titanium as the part of the mixed metals. Why we need to mix the titanium with other materials despite of the strength of titanium and the cost, which is not too expensive, I think. Yeah, so we need to mix it with carbide graphite to improve the melting point, so the material won't be easily melt and easily erode. And then we also need tungsten because the really high melting point and the metal properties of the material, but tungsten costs quite expensive, so maybe put a little bit of tungsten on the material. So in conclusion, the material mainly will be a mixed materials. but I think we can consider putting aluminum. I say before that aluminum is not suitable because of the low melting point and the low strength, but aluminum is cost really cheap, so I think maybe we can consider using it. But I think for rocket maybe don't, because the factor of safety. Thank you.
These are our references for our presentation. Thank you for listening.